I'm going to compute the gradient of the function phi of xyz is equals to xy cosine of yz. So the function that we are given there is a function of three variables. If we are having a real valued function phi of xyz, the gradient of phi, which we denote by grad phi, is the vector partial derivative of phi with respect to xi plus partial derivative of phi with respect to yj plus partial derivative of phi with respect to zk. So I can just go on and write my grad phi there, then substitute the phi that we are given here. So it's xy cosine yz. That's our phi there. And the next step is now to go on and evaluate the partial derivatives. So I'll start with the first one here, the partial derivative of phi with respect to x. So in this case, what we are doing there, we are differentiating xy cosine yz with respect to x, but taking y and z as if they are constants. So when you do that, the result that you get there is y cosine yz I. Then we go on to the next part of this partial derivative there with respect to y. We are differentiating with respect to y, xy cosine yz, treating x and z as constants. But in this case, we see that we are having a product of two functions of y there. So we are having xy multiplied by cosine yz. So we'd have to use a product rule, which says that u v prime is equals to u prime v plus u v prime. So I'm going to take the u to be the xy, then the cosine yz, I take it to be the v. And then go on and take the partial derivative of u with respect to y, and we get x. And then for the partial derivative of v, which will give us our v prime, is equals to minus z sine yz. So we have our partial derivatives there. Then we go on and substitute them here into our product rule. So when you do that, the result that we would get there is x cosine yz plus xy minus z sine yz multiplied by the unit vector j there. So that's for the jth component. We now move on to the next one. This one here, the partial derivative with respect to z. To evaluate this, we'll be differentiating xy cosine yz with respect to z, taking x and y as constants. And then just note the derivative of cosine az gives us a minus a sine az, where a is a constant. But in this case, we are taking y as if it's a constant. So the y there will multiply this y, and we would have minus x y squared sine yz k. So that's our gradient there, but we can simplify this part here where you're having x times y times minus z. It gives us minus xyz. So I'll write the first component, the one with the I there. Then the component with the j is the one that we are saying this highlighted part is becoming minus xyz. So we'd have x cosine yz minus xyz sine yz j. Then the component with the k is not changing, so I write it as it is, a minus x y squared sine yz k. So that's the gradient of the scalar field that we are given there.